Hello, let me begin by thanking the organizers of this meeting for the invitation to give a talk. And let me apologize for sending this talk so late to you, and I hope it's still useful. I will tell you about what I know. I'll try to summarize what I know in this talk about the moduli space of heterotic SU3 structures, or what's known about the whole Strominger system. Before I start discussing this, let me just mention my collaborators. What I tell you today is mostly written in these papers here, right? And of course, we are not the only ones who have been working on this. There are a number of people, for many, many years have been trying to understand the modular space of these systems. But these papers here actually have a very close relationship with the papers that I've written with my collaborators. In particular, this paper by Anderson, Ray, and Sharp is very closely related to this one here. And so is this one by Mario Garcia Fernandez, Roberto Rubio, Carl Kipler. This paper, also by Mario and Roberto Rubio and Carlos Shabazzi and Carl Kipler too, is closely related to this last reference here, in which we actually talk about finite deformations as opposed to just infinitesimal deformations of a system. So before I tell you the contents of the talk, I'll start by defining what the whole Strominger system is. So let X be a six-dimensional Riemannian manifold, and let V be a vector or gauge bundle, a vector bundle or gauge bundle on X with connection A. So a heterotic system, or the whole Strominger system, as I said, is a quadruple, right? That of a manifold, a Riemannian manifold. In fact, with a SU3 structure, a bundle B with connection A. We will also have a connection on the tangent bundle of X. And then there is this object H, which is a 3-form on X. So given this mathematical object, the whole Strominger system is a structure imposed on this object. And so I will tell you what these constraints are. So first of all, the manifold, the six-dimensional manifold, admits a certain SU3 structure, right? So where the little omega and capital omega are respectively a 2-form and a 3-form, where X is a complex and conformally balanced manifold. Right, so that means that the SU3 structure is not the most general SU3 structure possible. There are some constraints on them, which I will tell you in a moment. And in fact, this has to do with manifolds which are not complex manifolds, which are not Kähler, which is the topic of this workshop. So, but we are going to work not just with manifolds, but also with bundles on the manifolds, right? So we have that the bundle B, the connection, is such that the connection is an instanton. And by that, I will mean that the bundle is a holomorphic bundle, right? So it only has a 1-1 part that is not zero. So the 2-0 is, well, the curvature. Sorry, F is the curvature of the connection, and it's a 2-form, and the 2-0 part or the 0-2 part are vanished. So that needs to be holomorphic, and we will talk more about this in a moment. And also has a condition that says that the trace in respect to the Hermitian form is 0, right? So this is the Yang-Mills condition on the curvature of the connection. I said that in this system, we have also a connection on the tangent bundle, and we require this connection to be an instanton on the tangent bundle, meaning something analogous to this, right? So that means the tangent bundle has to admit a holomorphic structure, and moreover, it satisfies the curvature is the curvature of this connection is trace-free with respect to the Hermitian form. And finally, I mean, up to here, I mean, we're talking about bundles on complex manifolds up to here, right? Moreover, holomorphic bundles on complex manifolds and bundles that satisfy Yang-Mills condition, where the connections, the curvature of the connection satisfy Yang-Mills condition. But we have an extra complication, which is what I mean. This last condition is the one that has made progress in the context of heterotic compactifications hard. So not only we have so heterotic theories are Yang-Mills theories, right? So, but they also have this form. It's called the flux in these three-form flux, the three-form flux on X. But this flux needs to satisfy this condition. In the physics literature, is called the anomaly cancellation condition. But at the moment, we will just say that H is defined by this equation here. But notice the complication, right? So this is a three-form on the manifold. It is said that that this, apart from a closed bit, is equal to the difference of two Chern-Simons forms, right? This is the Chern-Simons form for A, and this is the Chern-Simons form for theta, where here's a reminder of the formula for the Chern-Simons form, right? This object here. This alpha prime here is a constant that appears in these compactifications that is non-zero and is small. It has to do with a perturbative expansion of the heterotic theory as a perturbative string theory. And this B here is the famous B field that some of you might be familiar with in type 2 theories. So in type 2 theories, the B field is a 2 form. In heterotic compactifications, this is not a 2 form. Right? It has two indices, and they are antisymmetric, but it's not a 2 form because it transforms on the gauge transformations, right? So if you perform a gauge transformation on the connection here, then on your gauge fields, right? Then this is not invariant, and so therefore this is not invariant either. But H is a 3 form. The whole thing is invariant under gauge transformations. So and what's even worse in terms of trying to solve finding solutions for these systems is that this should be equal to a torsion. So this T here is the total antisymmetric torsion of a connection compatible with the SU3 structure. Right. We will say more about this in a moment. So this equation is mixing up all your degrees of freedom in this system. So as you can see, I mean, one can opt up to here. One can use all the theories for deformations of holomorphic bundles. But once you add this, you are in trouble, right? And also, moreover, you have a Hermitian form here, and the formations of the Hermitian form, and one needs to be able to understand how one deforms these theories in a way that you get another holostrom in your system. In other words, that you preserve this structure. Right. So a couple of remarks, right? So heterotic G systems are Yang-Mills theories, as I said in a moment, and they are relevant to supersymmetric compactifications of heterotic superstrings. I'm using a G system here because today we're talking about the SU3 systems, right, pertaining to compactifications on 6-dimensional manifolds. But one can compactify in a 7-dimensional manifold, and it will be a G2 system, or on an 8-dimensional manifold, and you will have a spin 7 system, and so on. Um, so the other things I want to point out is that they are, on the face of it, they look rather different from type 2 theories. Though eventually through dualities, one should be able to map the structures in type 2 theories and heterotic theories. I mean, when one starts working on them, they look rather different. I mean, in the heterotic compactification, one has no D-branes, right? So you don't, so when you compactify a type 2 theory, say on a Calabi-Yau, you also have D-branes, that's non-perturbative corrections of your theory, and you need this to be able to get a non-trivial gauge theory. Without them, is this the type 2 theory on a Calabi-Yau at most has an abelian gauge symmetry, right? So gauge theories appear in a non-perturbative gauge symmetries or gauge degrees of freedom appear by configurations of D-branes on type 2. Whereas in the heterotic theory, you have them, they come with they are Young's theories in 10 dimensions. Right? So now I'm ready to tell you more or less in which order I will tell you about this space, these structures. First, I'll talk about the geometry of the manifold itself, right? And I will comment a bit on its infinitesimal deformations, or we will see that one gets a bit there are issues discussing that. But this, I mean, this is interesting on its own, right? Even without the bundles. I mean, as when one wants to study non-Kähler manifolds. So in our case, this would be non-Kähler manifolds with vanishing first Chern class. Those are the ones that will be relevant for us. Then we are going to write down the whole. I'm going to add everything else to this, the bundles and this anomaly cancellation condition. And I'm going to explain that the heterotic system, I mean, all those conditions that I just discussed, can be put together in terms of an nilpotent operator, right? So that you can find an operator acting on an extension bundle, on a relevant extension bundle, that whose nilpotency is equivalent to the heterotic system, right? So in physics terms, I mean, one can say that one is what one is doing is one is saying that the existence of an important operator is equivalent to the preservation of is equivalent to having the series with one supersymmetry, which is which is what the constraints that come about for the whole Strominger system are constraints that preserve one supersymmetry in 4 dimensions. And then later on, I'll tell you about the tangent space of the moduli space. And here I should perhaps add that, time permitting, I'll see how far I can go with this. I don't want to talk too much, so I might tell you more more if there is time. In particular, I would like to have time to tell you about the finite deformations as opposed to just the tangent space of the moduli space. Right. So as you see here, I mean, the tangent space of them, as I'm advancing here, once you understand how the heterotic system is equivalent to the existence of an operator, nilpotent operator that acting on forms on a certain extension bundle, then what one discovers is that the infinitesimal deformations of the system preserving the structure are those that belong to the first cohomology of this object. I mean, and this Q is the name I'm giving to this extension bundle. So let's start with the geometry of X and its moduli, or maybe not, right? So for the Strominger Hall system, what we want from X is that it admits a certain SU3 structure, but such that X is complex. So it has an integrable complex structure. I mean, generic SU3 structures are about almost complex manifolds with vanishing first Chern class. So so we are actually requiring that the complex structure is integrable. And there's another important condition is a condition that relates to the Hermitian form, this two form here. X, it is said that this two form needs to satisfy this condition. This here is a scalar called the dilaton, right? But what this says is that X is conformally balanced, right? So conformally, and this here is the conformal factor. Moreover, so the X admits a 3-0 form with respect to the complex structure, capital omega, that is holomorphic. It's a holomorphic 3-0 form. That's another way of saying that this manifold needs to have a vanishing first Chern class. So this is a mouthful. So I'm going to say that X admits a heterotic structure, meaning all this, right? Okay. So there is more. I mean, something that I already mentioned when I defined the whole Strominger system. On this manifold, I mean, in a manifold with an SU3 structure, there are connections that are compatible with the SU3 structure. In other words, that have is a connection with autonomy SU3. But in this case, there is a unique metric connection, nabla, with totally antisymmetric torsion, which is equal to the flux, right? So and if one computes it, what you find is that this is basically the d of omega, the exterior derivative on the Hermitian form, and acting with this is the action of J is the complex structure. This is the action of the complex structure on this 3 form, right? And this unique connection, this unique connection with total antisymmetric torsion, compatible with the SU3 structure, is known as the Bismuth connection in the mathematics literature. Okay, so you see in the definition, I mean, this theory, these heterotic theories have this flux, which is a 3 form, is totally antisymmetric, and the torsion needs to be, the torsion needs to be equal to that, right? So that's a very important constraint, but particularly when we will remember that this actually contains the gauge fields in there. So before saying more about moduli spaces or anything else, it's good to discuss examples. Or examples that are maybe examples, so it's not clear, right? So Calabi-Yau manifolds, of course, are examples, right? Except that these are Kähler, right? The omega is 0. So we want examples that are non-Kähler. A beautiful example, one that I've been wanting to get my hands on and work with it, is the case of connected sums of the product of S3 cross S3. And you need to have at least 2 of them, otherwise it doesn't work. So and these were discussed by Lu and Tian, and also by other people, and who actually proved that these admit a heterotic structure as we want. It's not highly non-trivial, right? So there are, of course, I mean, here, I mean, there are so many people there that I couldn't have it in this space. So perhaps I will add to my slides later a number of references about these other constructions. but many of them have to do with non-Kähler elliptic vibrations over Kähler surfaces, for example, like T4 or K3 or P2 or so on. And these are, most of them are based in the work by Hover, where he constructed a principle, torus bundles over surfaces, and this was taken by Goldstein and Prokuskin, and then Hu and Yau, and then Becker and Yau and Seti, and that's a number of people who did constructions and have done constructions of Kähler manifolds using this prescription. I'll do this. I will add this later. So 5, this is just a question. Perhaps the audience knows how to deal with this. So this is when I said examples, or maybe not, right? So let's consider the class of all manifolds which are bimeromorphic to Kähler manifolds. And this class is called the Fujiki class. They are all balanced manifolds, and this was proven in '93 by Alessandrini and Bassanelli. So once one has a class of at least in abstract, one discusses this class, the immediate question for us would be which manifolds of these have first Chern class? I mean, and is this useful at all? So in a way, if any of you know what to do with this question, I mean, that would be interesting. So the next example, I mean, I can tell you that I know what to do with this question in one case, which is the case with the case that has to do with flops. I mean, so this is an example. I mean, a basic example of a bimeromorphism, right? So so you take take for example any Calabi-Yau manifold, and take a rational curve inside a Calabi-Yau manifold and flop it, right? So this process, I mean, as we learned from Attia, preserves the vanishing of the first Chern class, right? Because there are no exceptional curves, so then the canonical class stays trivial. So the new manifold, you start with a manifold X, and you flop this rational curve, and now you get a new manifold X prime. What you find is that it's not necessarily Kähler, because one can prove that a generic flop generically creates curves which are trivial in homology. But one can prove that X prime is balanced, right? Because by the theorems of Alessandrini and Bassanelli, this new manifold is balanced, right? Because X and X prime are bimeromorphic and related just by a flop. So then any Calabi-Yau with a flopped rational curve will, in principle, is one of these examples that will have a heterotic structure, right? So this will work. And again, a question is, I mean, how useful is this? I mean, I haven't used it. I mean, I know this fact, but again, it's a question that anyone in the audience can tell me how this can be used. That would be great. Or maybe it's useless, and it would be good to know too. Another example, it seems I don't know how to count. This is the 7. This is example number 7, right? So 7, right, is Conifer Transitions from Calabi-Yau manifolds. I mean, how would that work? So experimentally, I mean, as we know, and this is related to the Reed's conjecture, right? Calabi-Yaus are connected to each other by what physicists call Conifer transitions, right? These are topology changing transitions that roughly go as follows. Suppose you have a Calabi-Yau manifold, right? Like this one in this picture, that has a number of 3 cycles, right? Like this here. I mean, suppose now you contract these cycles to a point. Right? So you start locally, I mean, if if you take a lens, a magnifying lens, and look at this closely, this looks basically like a truncated cone, right? Where the base of the cone is S3 cross S2, and you have you have here you have the 3 cycle that you are that is vanishing. So it vanishes, and then what you get is a Calabi-Yau. That's now a Calabi-Yau bias. This has singularities, but the singularities now are ordinary double points, right? So I could have started the other way around. I think that would have worked out better, in which I start with a Calabi-Yau that has a number of ordinary double points. One can prove that near those points, the manifold looks the locally. Again, if you zoom in around one of these points, what you find is that it looks like a cone, right? Where the base is S3 cross S2, and at the tip you have your ordinary double point. And going that way is the same as deforming your manifold, right? So then you replace the tip, you surgery, replace the tip by an S3. You can, on the other hand, what you can do is to do a small resolution of this point, and add instead at the tip of each at the tip where you replace the tip of this cone by a tooth field, by a rational curve, in fact, right? But when you do that in a generic way, I mean, this is not necessarily Kähler, right? I mean, you have, I mean, this is a very technical point. You have to alienate the small resolutions and do a number of flops in such a way that you actually get a Kähler manifold. But generically, you get a manifold that is not necessarily Kähler, right? And in fact, this manifold is balanced, right? Again, this is in Friedman's, I mean, it's another reference that I might want to add. This fact that you get a balanced example is in Friedman's work on these transitions, right? These topology changing transitions. So a sub-example of this is the example I mentioned earlier, which is the connected sums of S3 cross S3, right? Which gives you, I'm calling this MK, where K is the number of pieces that you have, right? The number of S3 cross S3s that you put together. And these are complex and balanced, but not Kähler, right? So Lu and Tian proved that these have complex structures with trivial canonical bundle, as long as K is bigger or equal to 2. These manifolds have these Betti numbers. B2 is always 0, so in some sense they are kind of simple. And B3 is always twice the number of factors, right? The number of S3 cross S3 factors. And to prove this, what they used is precisely a Conifer transition from a rigid Calabi-Yau manifold, right? So they started with the manifold is called the Schoen's manifold, and it's just a rigid Calabi-Yau manifold, meaning no complex structure deformations, and they did a kind of reverse Conifer transition to obtain these objects, and proved in this way that they are the kind of objects that we would be interested in. Right. Okay. So I hope that by giving these examples, I mean, in some ways, in an egocentric way, I might get some feedback, but also, I mean, I hope also that I have said something that is not entirely that is something that is new to the audience, that might be useful to produce more examples. So now let me say a word about the formation theory, right? So this is an issue with these manifolds, because, I mean, let me start by recalling what happens when you have a Kähler manifold, right? So Kodaira Spencer, a long time, Kodaira and Spencer, I mean, proved that the Kähler condition is stable under the formations of the complex structure, right? However, the balance condition is not. And the proof, unfortunately, is nice, but it's by counterexample. So this was done in the early 90s by Lebrun and Poon and by Campana. It's nice to know this, but you cannot learn under what circumstances one can preserve the balance condition. More has been written on this, but I don't want to dwell on this today. I just want to say the following. Suppose that we're taking one of these conformally balanced manifolds and we want to to, to study its infinitesimal deformations, right? But this is what you find immediately is that this is not necessarily finite dimensional, right? And this is not good for physics. So this is in a paper by Becker, Zheng, and Yau, which said the following, right? So consider this two form, right? That is apart from this conformal factor is the square of omega, right? The conformally balanced condition says that this four form is closed, right? So its infinitesimal deformations will be given by its Lie derivative, and let's consider infinitesimal deformations corresponding to a section of a vector V, right? Section of the tangent bundle. And because this is closed, a computation says that this Lie derivative is given by the derivative of the insertion of V on the four form, right? But then this insertion on V, if you just compute it, apart from the conformal factor, you get a one from here, wedge omega. But this is not the most general three form, right? A general three form is of this form here, right? This by the left is the composition. A general three form can be written as a primitive three form, meaning that contracted with the Hermitian form is 0, plus the non-primitive part, which contains a factor of omega and a one from A. Right. So here we have in this three form here, what we have is this object here. Is an object of this form, right? So this is not the most general three form. So we cannot say that we have closed four forms quotiented by exact. We cannot do that here. And so generically, this is infinite dimensional, right? So mathematically, yeah, that's fine. But perhaps that's not something the problem faces. This is not good. And of course, the problem physics itself when one considers the full whole Strominger system. Okay, so now for the second part of this talk, I would like to discuss how to rephrase the heterotic system in terms of an important operator. So let me start with a baby case, right? It's a well-known case. And this is what we are going to generalize, in fact. Recall that a manifold X with an almost complex structure is integrable if and only if the del bar operator squares to 0. So that's a nice way to express the integrability of a complex structure, as we know. So what we are going to do is to lift this idea to the heterotic system. Right? It is well known also that one can lift this idea just to a bundle, a bundle on the manifold, right? So recall also that a bundle B on X with connection with connection A, right, is holomorphic if and only if this del bar operator is squares to 0. Where this del bar operator with a sub A here is a covariant. Is a covariant derivative on forms with values in the homomorphisms of the bundle, right? Which has this form. I mean, this all is very natural, and it is not too difficult to prove that the squaring of this operator, the nilpotency of this operator, is equivalent to the fact that the 2-0 part of the curvature of A is 0. right? So what this means is the following for us. I mean, if we were only considering bundles with connections on these manifolds with heterotic structure, then means we can recast integrability of the complex structure on X together with the holomorphicity of V in terms of an extension bundle, right? Given by this exact sequence, the short exact sequence, which is holomorphic, and with extension, something I didn't put in the slides, is that with an extension class that I'm going to call curly F, which is the Atiyah class. So this is with extension class called curly F, right? And in fact, there is an operator I'm going to call the bar 1 acting on forms with values in Q1, which satisfies this, which is nilpotent. And this is of course all work by Atiyah, right? This is well known. So what we have is this extension bundle Q1, right? And this is the extension class, this curly F here. And the holomorphic structure is given by I written in terms of a matrix, right? Acting on forms on Q1, where these are the del bar operators that we have just talked about, and this is the Atiyah class, which is a map that maps forms with values in the tangent bundle of X, forms on X with values in the tangent bundle of X, to forms on X with values in the endomorphism of V, and more explicitly, this nicely here, more explicitly, the acting on a form with a form, say form 0Q with values in the tangent bundle, like this, is given by the insertion operator, right, of this object on the curvature of A. And so what is nice to see is that this is a holomorphic structure if and only if this squares to 0. And that is equivalent, if you work it out, I mean, you square this operator, you work it out that this squares to 0 if and only if this operator squares to 0, which is the integrability of the complex structure of X. This covariant derivative squares to 0, which is nothing but the holomorphicity of V. And there is an extra constraint that appears, right? But this is actually 0 automatically by the Bianchi identity of the curvature. Right, so this structure is all very nice, well understood. I mean, by Atiyah, and it actually paves is really the right setup, at least in our context, to discuss moduli, as we will see later. So, having said this, now we can extend this to include the instanton on the tangent bundle, right? So we have a holomorphic structure on the tangent bundle of X. So we define another extension bundle in which we extend the Q1 by the endomorphisms of the tangent bundle, and the holomorphic structure now contains a covariant derivative with respect to the connection on the tangent bundle, and this is what we have called delta 1, right? So this here is what delta 1 before, right? And these are here, so is the Atiyah class corresponding to the connection on the tangent bundle. And again, the squaring of this is equivalent to this extension bundle being holomorphic, and it puts together the integrability of the complex structure of X, the holomorphicity of V, and the tangent at the tangent bundle, and also uses the Bianchi identity for the curvature of the connection theta. Right. Okay, so I think with this background, we are now ready to understand what happens here for the whole heterotic system. But now I guess you can begin to guess what I'm going to do. But before I do that, let me say the following. What happens to the Yang-Mills condition, right? We also, not only the bundles need to be holomorphic, but we also need to satisfy this Yang-Mills condition for the connection A and theta. But we use theorems by Bourdain, Lee, and Yau in the 87 that generalize, these theorems generalize the work by Donaldson and Uhlenbeck and Yau in the case of Kähler manifolds. I mean, this is the same, basically a generalization of those theorems that apply for manifolds that are not Kähler. So these theorems guarantee that under certain circumstances, a holomorphic bundle always admits a unique Hermitian-Yang-Mills connection. That means a solution to this. There is a unique solution to this. I'm sorry. I don't want to enter into the technicalities of these circumstances, but what it means is that one needs to work with bundles which are polystable. I mean, and this is the property that these bundles need to have, so that you don't need to worry about having a solution to this equation. So only working with the holomorphicity of the bundles and imposing that you are working with polystable bundles, you guarantee that there is a solution to these equations, and therefore you have the full Strominger system, as we will see later. Whole Strominger system, right? So let's look again at the definition of the whole Strominger system, right? So I don't have to flip back in the slides, right? So we have a structure of this mathematical object, right? So we have discussed the fact that the manifold, system-Xenia manifold, has this heterotic structure, meaning all this, right? Conformally balanced and vanishing first Chern class. As a complex conformally balanced manifold with vanishing first Chern class. That A and theta should be instantons, right? So meaning that the bundles corresponding bundles are holomorphic, and that we have and there are traces with respect to the Hermitian form. The curvature is traced with respect to the Hermitian form. But we still have to deal with this kind of nasty object. Well, it's nasty and it isn't, right? It's nasty when you first try to work with it, but then I think this setup that I have been describing will deal nicely with this extra condition, right? So we have, just as a reminder, right, that we have this flux that mixes up all the degrees of freedom, right? The gauge fields with a new degree of freedom associated to the B field, this is all related to the torsion, to the Bismuth connection on the manifold. So the idea, as you can guess now, is to construct an extension bundle, Q, an extension bundle of this bundle E that we had before, by something, right? And an operator, del bar, d bar, which acts on forms with values in Q, such that the nilpotency of the nilpotency of the operator gives you the whole Strominger system, right? So we expect to have something like generalization of what the work by Atiyah, in which you have an extension class, and I'm going to call curly H. And of course, in this corner, you will have another operator, and I will tell you now what this should be. I mean, I won't tell you, I mean, how we found it, but I will just tell you the answer. So before that, let's remark the following. Take the exterior derivative of the anomaly equation, right? This equation this equation here, the anomaly cancellation condition. We'll take the exterior derivative here, this is 0, and then we get the D of the Chern-Simons forms, right? So then what that gives you is that the D of H is, apart from this constant, is the trace of S squared minus, there's a typo here, right? Minus the trace of R squared, right? All together here. And that should be, of course, the D of the torsion, the torsion of the Bismuth connection. So when you do that, I mean, in the physics literature, this is called the Bianchi identity of the anomaly cancellation condition, right? So now part of the idea in generalizing the ideas by Atiyah to this context is that one wants to find a map, right? So this analog of the Atiyah class, right? The maps forms with values in this bundle E to form with values in this unknown here yet, for which this identity, by this identity I mean this Bianchi identity, plays a role similar to the Bianchi identity for F and R in the case of the nilpotency of the operator of the operator associated to the nilpotent operator associated to the bundle E. Right. So the answer is the following. So the whole Strominger system on this object, right, is equivalent to the existence of a holomorphic structure, D bar, on the bundle Q, given by this exact sequence, right? Where by this short exact sequence. So what this means is that topologically, Q is going to be the sum of the bundle E, the direct sum of the bundle E, right? Plus the cotangent space of X. So we are expanding E by the cotangent space of X. I mean, what we found that was the natural thing you need to put here to extend E, right? To get the right the Strominger whole system. And the extension class, which I was calling curly H before, I'll define it in the next slide. And but so that the holomorphic structure on Q is given by this operator here, right? Where this is just a reminder what this del bar E is, right? Where here is just the del bar operator on forms with values in the cotangent bundle of X. Right? So now, of course, the big missing piece is what this extension class is, right? So it maps. So H is a map. It maps forms with values in E to forms with one degree more with values in the holomorphic cotangent bundle, right? So if I call X a form with values in E, well, this maps this to H acting on X. And the formula, I mean, it looks nasty, but it's not so nasty. I mean, it's for H is this. And so X, so if you take each piece in X here, right? So H on the delta here, this here, this delta here is a form valued in the holomorphic tangent bundle of X, right? And what it does is that it inserts this delta on the torsion. Then if alpha is a form with values in the endomorphism of P, then the H on alpha, it gives you the trace of alpha wedge F, and similarly for the tangent bundle. And what we prove is that this is in fact good in the sense that it's a well-defined map between cohomologies, not just between forms, right? It maps cohomologies into cohomologies, and under its gauge invariance covariant as under gauge transformations, this map here changes only by a del bar exact part, right? So again, now if you square the operator, what you find is that it does square to zero. It gives you the whole Strominger system, right? At least for the bundles, we have this. We already seen that for this, but also it gives you this extra constraint here. But this one is true by the Bianchi identity of the anomaly cancellation condition, right? By this Bianchi identity. So it all works out. So the labor was, I mean, finding that one needs to extend by the cotangent bundle, that wasn't too hard, but finding an extension class that actually, so that is equals to zero using this, I mean, it was a little bit of labor, but I mean, we put all this together in a theorem in our papers, so it's all good, we think. But, so now I think I'm ready to start talking about infinitesimal deformations. So again, we will, as you can, I mean, if you're familiar with the work of Attia on holomorphic bundles and deformations of holomorphic bundles, you will almost be able to guess what we're going to do. I mean, we're going to leave those ideas to the Strominger whole system. If we, so again, let's suppose we were only considering a bundle on X, right? A bundle with connection on X. In that case, and we were asking about infinitesimal deformations of this structure that preserve the holomorphic structures that we started with, right? So that preserve the structures that we want to have. So then we will, I mean, Tia will say, right, that then what you do, you discuss that in terms of deformations of this bundle Q1. So remember that Q1 was the extension of the tangent bundle of X by the endomorphisms of P, right, with class F, right, with extension class F. Sorry, what's happening here? Right? So this is just a reminder of what Q1 was. So so the deformations of this bundle preserving preserving holomorphic structure are given by that one can prove. I mean, even in a very pedestrian way, one can prove that they are given by the direct sum of the deformations of the bundle itself, but of course deformations that preserve the holomorphic structure, but also we are also deforming simultaneously the complex structure of the manifold, right? So we can, but Attia tells you is that of course you cannot allow for all possible deformations of the complex structure of X that preserve integrability of the complex structure, because some of those do not preserve the holomorphicity of the bundle, right? So this kernel of F is precisely the condition, is the condition that picks from all the possible deformations of the complex structure, it picks those that preserve the holomorphicity of the bundle, right? So these are of course obstructions to the formations of this whole structure to preserve holomorphicity, right? So the ones that are not in the kernel, right? So when it's so this is so this is what this is doing here, right? So what you have is a subspace of the deformations of the complex structure, infinitesimal deformations of the complex structure on X. So now we are going to leave this again to the heterotic system, and of course, I mean, I'm just going to state the answer. I mean, this is, I mean, this is not just that you just lift it, because I mean, in some sense you can, because you're talking about a holomorphic bundle, right? So you can use you can use that, but it's we also did it in a pedestrian way. It's not so simple, because you need to understand the deformations of the Hermitian form that you have there, right? So so when you leave this to the to the whole Strominger system, what you find is the following: that the infinitesimal deformations are in fact given by the first cohomology of the bar operator, right? Which right. So it's acting now on, of course, on one forms on with values in Q, and it has two. You can prove that this is a direct sum of two parts. One is the formations of the holomorphic structure, right? But again, as now again you have now to take the kernel of this class, right? And this is contained in the deformations of the holomorphic structure of E, right? That we had before. And then we have another piece that has to do with the formations of the Hermitian structure. So this here corresponds to the formations of the holomorphic structures, but we also have the Hermitian form. So this is the beauty of this extension, right? That by choosing precisely an extension as we had before, an extension by the cotangent bundle, then we are able to discuss the properties of the Hermitian form and its deformations. So what you find is that you have in this. Let me ignore this technicality for a moment. Actually, let me ignore it today. So it's basically given by the first cohomology of the Bar operator with values and on the cotangent bundle, right? So here we are talking about objects that have that are one forms, but they also have an index associated to the fact that they have values in fact in the holomorphic cotangent bundle. So these deformations are deformations of the complexified Hermitian structure. So this is something similar to what happens in type 2 theory, is that your B field always comes in a complexity that actually, let me say it the other way around, that your Hermitian form, say on a Calabi-Yau, always comes complexified. I mean, and in this case, the Hermitian form, the variations of the Hermitian form, right? I mean, by this, by this del T representing a particular variation of the Hermitian form, but it comes complexified with variations of the B field, but with alpha prime corrected variations of the B field, in fact. So this curly B here, is not just a variation of the B field as it would be in the type 2 theory, where you wouldn't have, in that case, you wouldn't have these terms there, but now we have it, right? So this complexification of the variations of the Hermitian form are variations of the B field together with terms that contain the formations of the bundle of these alphas and kappas here are deformations, correspond to the formations of the gauge potential of the gauge fields, right? So these are one forms with values in the normorphisms of B, and something analogous for kappa here, right? I mean, one can check that this is consistent with, if you try to vary this by hand, this is consistent with what I'm writing here, right? So that's what you find. I mean, that's very nice. I mean, there is a split in some sense between the holomorphic structures and the Hermitian structures, the formations of the Hermitian structures in this, at least infinitesimally. So unfortunately, this is all I can tell you about today. I run out of time. So let me just finish with some conclusions. So further work has been done after the understanding of this the infinitesimal deformations of the whole Strominger system. And this work has to do with understanding, of course, what happens when you have finite deformations, or what's the analog of the Moret-Cartan equation for complex structures, right? So in fact, there has been work already on the analog of the Moret-Cartan equation and Polaris-Spencer theory for the whole Schrödinger system. And this leads to a very beautiful structure that associated to an L3 algebra and an analog of the holomorphic Chern-Simons theory. And so this could be the subject of a whole other seminar. Um, there has also been work on trying to understand better the structure of this moduli space, and it is known that a Kähler metric has been constructed on the moduli space. The fact that the moduli space is Kähler, it was a prediction from supersymmetry. N equals to 1 supersymmetric theories are supposed to have a moduli space which is Kähler. And this is, of course, not obvious at all. I mean, how do you write down this Kähler metric, right? And so, in fact, this has been constructed, and it is surprising how the Kähler potential for the Kähler metric looks very much like the Kähler, the one that you will write just for a compactification of a type 2 theorem, a Calabi-Yau. The difference is that as you vary this Kähler potential to get the metric, you in fact need to vary, for example, the Hermitian form, and this then couples to the gauge bundle in a very clean and elegant way to give you also the metric on the bundle, right? So again, this is another pretty story, and here are some references, I mean, in relation to this work. There is a lot to be done in constructing examples, right? So here I actually have started putting examples here, but what I have, as I promised earlier in the talk, is that I was going to write at the end of the talk a number of references, which I will show you right now. I mean, there's more references as promised in slide 8, but also in this slide, right? But these are of course not exhaustive. I mean, there are many people who have been doing work on this in the last 15 years, in fact. But there is still a lot to be done in constructing examples and trying to understand I mean, in constructing examples, one also wants to compute these cohomologies, and how does one do that? There's a bit of work to be done there. Then, of course, in physics, we want to understand the quantum theory, right? It's not just the classical theory. I told you a story that already has quantum corrections, but they're associated to a perturbative string expansion. I mean, this alpha prime number that you saw in the slides, it has to do with that. But there are also non-perturbative quantum corrections, and how do one understand this? I mean, in the heterotic string, as I said earlier, we don't have D branes, but what we do have is NS5 branes, which type 2 theories also have, but they are all there, and then there are also sigma model instantons. So how does this affect the structure of the moduli space? How is this affecting this structure that we are talking about? So for example, the anomaly, so if you have a configuration of 5 branes, then what that means mathematically, at least in part, what it means mathematically, is that this Bianchi identity of the anomaly cancellation condition that we had before, that we saw earlier, gets an extra term that has to do with a form, a class that appears in how brain wraps so manifolds of the manifold X. So how does one understand this, and how is this changing the structure that we have just discussed? In other words, can we lift when we add non-perturbative corrections? Can we lift this structure that we have in terms of this potent operator to include these effects? And then the last part I want to talk about is the last note. Perhaps I think the last note remark I want to make, I think, to finish this talk, is that of course to learn about non-perturbative corrections, one tool that we have at hand is dualities. But this in itself is complicated. How could we discover dualities with other theories? If we consider, instead of a 6-dimensional manifold with these three structures, one can consider instead compactifications on K3 or K3 times T2. It is enough to have a conformal K3 metric here, in fact, for in this case. So this is the case. This line has to do with theories with n equals to 2 supersymmetries. It's more supersymmetric, has more structure. But then there is a nice conjecture in physics literature that these theories are dual to type 2 theories on Calabi-Yau manifolds. Right? So there is a string of dualities here that if you take that happens under certain circumstances that I cannot describe at the moment, but under nice circumstances, you have this string of dualities, and it relates a type 2A with a Calabi-Yau, with some heterotic compactification of a K3 times T2 on a bundle and a bundle B. So this here is a bit like a heterotic SU2 structure, this one, right? And of course, by mirror symmetry, there should be also a duality with the type 2B on the mirror of the Calabi-Yau X. Right? So it's perhaps understanding through what we already know about the non-perturbative corrections, the non-perturbative quantum theory on this side. Perhaps one can learn something about this. And I didn't put any references. There is a long string of references of people who have been working on this, in fact. So, and then finally, there is also the one important duality in type 2 theories that I have just mentioned is precisely the mirror symmetry. Right? So the question is whether in the heterotic is this, right? Whether there is a concept of mirror symmetry in the heterotic or a generalized notion of mirror symmetry. And by that, I mean that if you have your quantum field theory on a heterotic, on a given heterotic system, I mean, and another quantum field theory on another heterotic system, under what circumstances the quantum field theories are the same. That means that the spectrums will be the same. It means that the correlation functions with quantum corrections will be the same. Right. So this is extending the concept of mirror symmetry in the heterotic context. And people have already been working on this. In fact, I mean, these are newer references, but people have already been working on this for a while. In this notion of what's called the 0-2 mirror symmetry, because it's referring to the supersymmetries of the two-dimensional sigma model of the string. Well, I think with this I finish, and thank you for your patience, and I hope that this has been of some interest, at least for some of you. Thank you very much.